Hello, everyone. Welcome to this VChain Bootcamp webinar. I'm Peter Zhou. I'm the Chief Scientist of VChain. Today, I'm going to co-host this webinar with my colleague, Dr. Max Ran. So Max is a senior research scientist inside VChain's team. So Max, would you like to say hi to everybody?
Hi, this is Max.
Okay, so this webinar is going to consist of 3 parts. The first part will be me talking about the current proof of authority consensus. The next part will be Max talking about PoA 2.0, which is the next generation of PoA. So we will have a Q&A session in the end. So I will start my part first. The title of my presentation is What You Might Not Know About PoA Yet. So today I'm not going to touch on many technical details of PoA. Instead, I will focus on answering some important questions about PoA, which I feel like our community members and business partner may ask and care about. So I've put 3 questions here, which I'm going to answer. So the first question is, of course, what is PoA? So I'm going to give a high level to this question, and I hope my answer could help you to better understand my answers to the following questions. I'm Peter Zhou. And my next question is, does PoA make Vision Thor scale? So scalability is a very important problem from a consensus point of view. And so PoA is essentially a set of rules. The thing is to decide to which block should nodes to attach the. So let's first look at the first question. If you want to be a miner, or in other words, if you want to be go through a KYC procedure, pass all the qualification checks, and be approved by the board of steering committee. So PoA maintains a list of all the nodes that have been authorized on chain by a smart contract, and it randomly selects one node from the list to generate the next new block. And each node on the list will have equal chance to be selected. Now for the second question, we may in practice have the situation, for example, like the one I put in the picture on the right. Here we have 2 blocks marked in red and green. They are competing with each other. So the system needs to know which one to choose to attach the new block. So PoA computes a quantity called total score and put that quantity inside each of the blocks. And it says we should choose the block with the largest total score value if there are multiple candidate blocks to choose. Now, I'm not going to explain how we're going to calculate this total score because it's quite technical. So simply speaking, total score is a value that is accumulated block by block from the very first block to the latest one. Okay, let's go to the next question. So I've seen people criticizing PoA because it requires the miners to be authorized. They argue that it is against the idea of decentralization. So the question here is, does PoA make Vision Thor less decentralized than other major public blockchains? So to answer this question, we need to first understand the word decentralization means. What the word decentralization means here. So I want to make sure that we are on the same page before I tell my answer. So by definition, decentralization is the process of distributing and dispersing power in a system so that we don't have to rely on a central authority to make decisions. So that's really think about what kind of decisions we need to make in a public blockchain system. We all know that blockchain technology allows us to write decision-making rules inside code. So most of the decisions can be automatically made by blockchain code itself. That brings us a great level of decentralization. But there's one thing blockchain node cannot decide. That is, it can't decide what are the pending transactions to be packed in the next new block. So it is not hard to see that the power of making such decisions is equivalent to the power of producing new blocks, or in other words, the mining power, because you have to get the right of produce a new block, then you get to choose what are the pending transactions to be packed in the new block. So the blockchain system uses its consensus algorithms to distribute mining powers to miners, and the miners select pending transactions of their own choices when they produce new blocks. Now we know that when we compare the level of decentralization of two public blockchains, we actually compare how the mining power is decentralized within these two systems. So for example, if we say a public blockchain A is less decentralized than a public blockchain B, we actually mean that the mining power is more concentrated in system A than it is in system B. So is it true that VeChain Thor is less decentralized than other major public blockchains? So to answer this question, we have to look at how mining power is decentralized in these systems. So let's first look at Bitcoin. So Bitcoin is using proof of work consensus. The mining power is distributed proportionally to how much of the computational power you have, or in other words, how much of the hash rate you have. The more hash rate you have, the more likely you will be the one to produce the next new block. So based on the Bitcoin rules on paper, anyone can participate PoW to compete with others for the right to produce the next block. And anyone can keep anonymous by doing so. I think this might be true at the very beginning of Bitcoin, when you can just use your personal PC to mine Bitcoin in your basement. But today, I don't think this is the case. Today, Bitcoin is being mined by professional companies. And there's one interesting thing, that even those professional mining companies, they don't directly participate in PoW. So instead, they delegate their hash rates to mining pools to maximize their profits. And it's actually these mining pools, they are competing with each other for the right to produce new Bitcoin blocks. So at the time I'm writing this slide, I wanted to know how much of the hash rates those top mining pools are controlling. So I visited btc.com and I found a figure which I copied pasted here. So the figure shows you the percentage of the total hash rates across the whole Bitcoin network the top mining pools were controlling in the last 24 hours. So I did a little bit calculation here, and the results show me that the top 5 mining pools control 73.8% of the total hash rates, and the top 14 mining pools controlled 99.98% of the total hash rates. I also found that all of the Bitcoin blocks were generated by one of the 14 mining pools in that 24 hours. Okay, next let's look at the Ethereum network. Ethereum is also using PoW, although it is switching to POS in future. So based on the data I found, within the same period of time, once again, the top 5 mining pools controlled approximately 74% of the total hash rates, and 99% of the Ethereum blocks were generated by only 13 nodes in that 24 hours. So for public blockchains using POS as its consensus, the mining power is distributed proportionally to the amount of tokens you have. The more tokens you have, the more likely you will be the one to produce the next new block. In those ecosystems, there are staking pools that are functioning similarly to mining pools. So token holders can delegate their tokens to the staking pools to maximize their profits. So basically, it's the same story. The last thing we want to look at is EOS. So EOS is the largest public blockchain using PoS consensus. So in EOS, the mining power is evenly distributed to 21 EOS nodes. So these nodes are called super nodes, and they are voted by EOS token holders. Now, I did a little bit study about EOS governance, and I found that a lot of the super nodes were owned by crypto exchanges and the mining pool companies. And there is clear evidence showing that these super nodes, they're trying to consolidate their power through colluding and vote trading. So I will talk more about EOS in my future webinar about blockchain governance. So if you are interested, please stay tuned. So based on all these numbers and the facts I found and show you, I can confidently say that there's no evidence supporting the claim that the mining power is more concentrated in VeChain Thor than it is in other major blockchain projects. So the conclusion is that we should firmly reject the idea that VeChain Thor is less decentralized. Okay, let's get to the last question. So before I answer how PoA scales, we need to understand how consensus of a blockchain system can affect its scalability. So by definition, the scalability is the capacity of a blockchain system to process new transactions. And it is often measured in terms of transaction per second, or TPS. So let's look at how we can estimate TPS. Suppose we have two blocks, block A and block B, and you want to estimate TPS within the time between the two blocks. So what we do? So the first thing we do is we count how many transactions packed in block A, and then we divide this number by the time between the two blocks. So this equation is probably something we can all understand. But there's one thing we might not realize, that by using this equation to calculate TPS, we are actually making an assumption on block A. That is, we assume that block A is not a temporary fork, which means block A is on the main chain of the blockchain and will eventually become a part of the global ledger. So if block A was a temporary fork, then the time and the network bandwidth used to transmit block A would be totally wasted, and it would not contribute to the blockchain's TPS at all. So having understood that, so now we can talk about how consensus affect TPS. So there are two principles. The first principle says the less time it takes blockchain nodes to complete the consensus process, the higher TPS the system can possibly achieve. Now, the second principle says the less chance of having a temporary fork in the system, the higher TPS we can possibly achieve. Now, let me explain why. So for the first principle, we can think a blockchain as a system that is constantly producing new blocks at a relatively steady speed. For example, VeChain Store produces a new block every 10 seconds, and Bitcoin produces a new block roughly every 10 minutes. So let's have a look at the picture again. So between block A and block B, to make the system working, blockchain nodes actually have to complete many tasks. For example, they need to propagate block A to other nodes. They need to validate block A, update their local ledger, They need to participate in consensus and complete the consensus process. And if the node is selected by the consensus to produce the next new block, it will have to take time to prepare the new block. So basically, there's a lot of things have to be done within that limited of time. Now, if it took less time for the blockchain nodes to do consensus process, so that means blockchain nodes have more time to do other things. So it's very likely that the blockchain nodes will have longer time to transmit block data, which means the block, in this case, block A can be larger because you have more time to propagate it across the network. And since it's become larger, we can pack more transactions in that block, which will result in higher TPS. Now I'll explain the second principle. So remember, a block is a temporary fork if it is not going to be part of the global ledger. So all the time and the network bandwidth will be wasted to transmit the block, which is actually useless. So the less time we have a temporary fork in the system, that means the more time and the more network bandwidth the blockchain nodes will have to transmit those blocks that will become a part of the global ledger, which will result in a higher TPS overall. Okay, so now I can explain how PoA scales. So basically, PoA tackles the problem of scalability from the perspective of the first principle. Remember that the first principle says the less time it took blockchain nodes to do consensus, the higher TPS we can get. So POS, according to POS design, it requires no computational competition, nor does it require any communication between blockchain nodes. So POA minimizes the time for blockchain node to do consensus. So theoretically, PoA could achieve optimal scalability if there was no temporary fork. In other words, PoA could outperform most of the consensus algorithms in terms of scalability if all the authority mass nodes kept being synchronized and functioning correctly. Of course, in practice, we don't have a clean sheet. We don't have a clean sheet of temporary forks. That means we will have temporary forks from time to time, but the fork rate is really, really low. So that is why VeChain Thor is enjoying a high throughput at the moment. Okay, so overall, I would say PoA scales pretty well. Now I want to talk a little bit about PoA 2.0. So in the past 1 year, Max and I have been working very hard to try to improve PoA. So our goal is to make PoA to achieve near optimal scalability most of the time, even in a more hostile and unstable environment. So the basic idea is to trade limited communication overhead for a much less theoretical chance of having a temporary fork. So overall, we will have a higher throughput. Now, the outcome of our joint research is PoA 2.0. So from a user's point of view, PoA 2.0 can bring us faster transaction confirmation and block finality. So before I finish my talk, I want you to know that PoA 2.0 is actually a highly advanced consensus algorithms. I drew a picture here so you can see we can categorize most of their consensus algorithms into 3 generations. The first generation is POW, and our current PoA consensus belongs to the second generation together with many well-known consensus designs. And we consider PoA 2.0 or surface as a third generation consensus because it takes the optimization of network bandwidth into account so that we can further improve block scalability. So I guess I should probably shut up now and let Max to continue our discussion on PoA 2.0. So thank you for listening, and I hope you have all now have a better understanding of PoA. So yeah, it's your turn, Max. I will stop sharing.
Hi. Can you see my screen now?
Yes, I can see.
Okay. So I will follow Peter's talk and introduce a bit more detail about PoA 2.0. So as Peter has just introduced that, let me move this away. Okay, so so we want to achieve a higher scalability. That means that we, as Peter has introduced the definition of scalability, we want to have more transactions to be sent in, to be confirmed or to be sent in a certain block interval. And by currently, the bottlenecks is mainly on the bandwidth. So it's mainly really on how much transaction we can send. It's not on the storage, it's not on the computation, but on the bandwidth. And then basically the bandwidth is fixed. So whenever you have, let's say we fix our 101 nodes, or we have already chosen our network for any blockchain, then your bandwidth is, the network capacity is fixed. There's nothing, not much thing you can do to improve the bandwidth. So the only thing we can do is to get better usage of the bandwidth. So let's see what is actually happening within a round, within this 10 seconds. So first of all, we take a few seconds to transmit the block. And during this transmission, some of the time is not related to the actual transmission of the transactions. But for example, the block header, or maybe some times required to establish the link. So this is the black part in the beginning, which is the communication overhead. And the blue part is the time we use to transmit the transactions. And after the transactions are received, nodes take some time to validate the block. And then they run the consensus process to determine who will generate the next block. So this is what's happening in this 10 seconds. Well, as we can, as I said, we want to make a better usage. So we want the blue part to be as much as possible. So the first technique we use in PoA 2.0 is that we use delayed validation. So instead of validate the block received in this round, we validate the block received in the previous round, so that the validation and the transmission can be done in parallel. And then we also use something called epoch-based random beacon. So instead of just compute who is the next round leader in the previous round, we already compute that one epoch ago. Epoch is it's a relatively long period of time, so usually 1 day. So in 1 day ahead, you already determine the schedule of the next day. So we don't need to calculate who is in charge of proposing block of the next round now. And now it seems that we can use the whole block interval to transmit block. But is that really so? So assume that in a normal network condition, you can send a 10 megabytes block in 10 seconds, normally. So what would happen if we set block size to be exactly 10 megabytes? The thing that would happen is that, okay, so for maybe the first guy publish a block, and the second guy receive the block, be able to receive the block in 10 seconds. And the third guy just a few seconds short to receive the second block in time. And what the thing that he can only do is to append his block to the first block. And then the fourth block, maybe there is a network disruption, minor network disruption, then he has to append his block to the second block because he couldn't receive the third block in time. And so a fork is created. Well, yeah, so in this time, Peter has already explained this is very bad for the throughput, because as we can see that some of the blocks will eventually not be on the longest chain, but they waste bandwidth to be broadcast. But then it is actually even worse because so think about how the adversaries want to attack the system. They want to double spend. The way they double spend is they secretly mine a chain. And at a certain moment, they publish the chain. Because of that chain is longer than the one in the public. The one in the public got replaced, and some of the malicious nodes confirmed transaction will be reverted. That's when a double spending happened. However, we said this is not very likely to happen as long as the malicious nodes control less than 50% of the mining power. Well, but that only holds under the condition that all the honest nodes are working together. Well, then the fork is exactly the situation that the honest nodes are not working together. The honest nodes are actually working against each other, and part of the mining power is wasted. They are not protecting the security of the system. And so to make it simple, fork is bad. It's not only cost bandwidth, it's also degrades the security of the system. So whenever a fork is appearing in your network, so although that's in Nakamoto consensus, like in Bitcoin, we allow fork to happen, but actually whenever a fork happens, the sum of your mining power is wasted and your security of the system degraded. And if you really look into the theoretical proof of almost all the consensus or Nakamoto consensus algorithm out there, they always assume that their fork rate is in principle very low. So for 99% of the time, there is no fork. Then the nodes are well synchronized, so they can there is naturally no fork. And then their security proof could hold. And in order to guarantee that usually there is no hold, no fork, they cannot send a 10 megabytes block in 10 seconds. The only thing they can do is maybe send a 5 megabytes block, and then they reserve some redundancy so that they can guarantee for most of the time there is no fork. And these are many consensus algorithm use this strategy, and they force into what we call scalable consensus algorithm. Well, they are part of the scalable consensus algorithm, what I call leader selection based algorithm, including our PoA 1.0. It is called scalable because it is better scalable than Bitcoin. So Bitcoin has other constraints, and this type of algorithm gets rid of that constraints, but they are not yet optimizing the bandwidth usage. Well, there are other algorithms like DAG-based algorithm or BFT algorithms which trying to solve the fork problem, but they failed to solve it completely. So for example, BFT algorithms solve the fork problem because BFT naturally don't have fork, but BFT has a loss of has a higher communication overhead. So yeah, let's make it more specific. So BFT stands for Byzantine fault tolerance. So it's a problem about how to reach agreement in an untrusted network. So basically exactly what Bitcoin is trying to solve. The only difference is that BFT is a problem originated in 1980s. So it has already been well studied before Bitcoin, and the BFT algorithm can also be used as a blockchain consensus algorithms. Somebody might know BFT as a slow algorithm, especially in the large network, because classical BFT algorithms like PBFT are really performed poorly in large networks. However, the BFT algorithms I mentioned here, like Tendermint, Algorand, and hot stuff, they are performing quite well in large network. Well, the only difference between BFT and Nakamoto consensus algorithm is that BFT do not have fork. So every block they propose is final. It is the final consensus. But in order to reach the final consensus, they need the multiple rounds of communication through the whole network. So let's take hot stuff, for example. In order for the block proposer, so the block proposer first propose a block. So in order for him to make sure that everybody has agreed on this block, he need to collect 60, well, in our network of 101 nodes, then he need to collect 67 signatures. Well, but then he need to make sure that everybody has agreed on this block. So it's not one round of 67 signatures, but 3 rounds of 67 signatures for him to be sure that everybody knows this one has reached absolute consensus. So it means in the black part, there is a large bandwidth communication overhead. So 3 times 67 signatures in order to get one consensus. And that's why I characterize them all into the second generation consensus, because for Bitcoin, the first generation consensus, there is a hard requirement that the PoW contention time need to be much longer than the blue part, so the transmission time. So which makes the performance of Bitcoin very bad. And the second generation consensus, including the one I mentioned, leader selection, DAG, BFT, solved that problem, but they not yet optimize the transaction, the bandwidth usage for transaction. Like leader selection has a redundancy, and DAG, they get rid of the redundancy caused by fork, but DAG has a problem of transaction replication. And BFT, as I just said, has a large communication overhead. And now we present Surface, we propose Surface, which stands for Secure Use Case Adaptive Relatively Fork-Free Approach of Chain Extension. The first catch in here is relatively fork-free. So we really are addressing the problem of fork. So we know fork is bad. Fork is bad for throughput and security. But we don't want to go to the extreme of BFT to make absolutely no fork. We take an intermediate approach. So for the sole leader case, if there's only one leader, whenever he's out of sync or he is malicious, he could create a fork. And for BFT, it took 3 rounds or 2 rounds of 67 signatures to make sure there's absolutely no fork. Well, what we do is we randomly select a committee of a small size to endorse for a block, so they help the leader of the round to propose a block. And then the probability that a fork would happen will be decreased to, like, for example, 1%. So 1% chance of fork is not sufficient for us to claim this one is final. So we still take the traditional approach of Nakamoto consensus, saying that this block will be confirmed after a few blocks. However, 1% of chance of fork is already good enough for us to safely remove the redundancy reserved to prevent fork. Why is that? It's because for the most worrisome part about a 1 leader case is that if we set the block size to 10 megabytes, whenever the fork whenever the round leader is malicious, when he observes, okay, the block size is too large, so 10 seconds is only enough for you to broadcast 1 block in a round, then he simply creates a fork. So he proposed 2 blocks, and he knows that your network is partitioned. But if the chance is reduced to 1%, that means the block leader has to work with a randomly selected committee, to work together with a randomly selected malicious committee to do that, which the chance is to be successfully create a fork, but the chance would be very low. So it will be economically not rational for him to perform this attack anymore. That's why we can safely remove the redundancy, because we know that the leader wouldn't have the incentive to do this attack. And also it's use case adaptive, means we are really looking at how to optimize the bandwidth usage. So for BFT, it's 67 times 3 signatures in here, in the black parts. But in Surface, you can adjust the committee size. So it may be just 6 or 7, depending on your network condition, it may be 6 or 7. And basically you can treat latency for throughput. So if you want a lower latency, you want near instant confirmation, then you can simply choose the committee size to be large as BFT. Then you basically got a BFT. But if you want a higher throughput, you can choose a smaller size of committee, and then you get a near scalable proof of work type of size of overheads. And then the reason why we call this a third generation consensus, well, it's because it always comes to us as a question, that's how is your consensus, or how is Surface different from all the other consensus algorithms? Especially people think all the other consensus algorithms talking about scalability. They talk about the super high TPS, or they have these fancy schemes like DAC. And it seems nobody is actually paying attention to the optimal optimized bandwidth usage. So why are you doing that? Well, the reason we are doing that is because basically our PoA 1.0, although that is looks very simple performance-wise, they are on par with all the other consensus algorithm I listed here. So it doesn't, TPS really doesn't show anything, because you can easily achieve a 10,000 TPS in the laboratorial setting. But if you, what I mean is that the second generation consensus, if you took any one of them out of the list and put that into our network, it would have a significant improvement or difference from our PoA 1.0. That's because that all the second generation consensus focusing on having a better scalability than Bitcoin, instead of, but not yet optimizing the bandwidth usage. And in Surface, we really focusing on, because we already built on the second generation consensus. So we use several techniques. I haven't introduced block decomposition, but it's another technique to improve, to make better use of the bandwidth. But all the other technique for a sole purpose of having a better use of the bandwidth, that makes it, well, that makes it like we can safely say that if you put any consensus algorithm into our network or any network, you couldn't have a better performance than Surface. Well, and then if we look at latency, as I just said, you can trade latency for throughput, but since we include a committee, our confirmation time will be shorter than classical NC, or it will be shorter than our old PoA. And now let's just take a look at BFT. So BFT is a bit different because it's achieved definitive consensus. But in order to achieve definitive consensus, it needs multiple rounds of 67 signatures, and you don't expect that to be collected in 10 seconds. A reasonable assumption in a network of 101 nodes would be maybe 2 or 3 minutes. Well, but the good thing about BFT is once, if you use some really asynchronous BFT algorithm, once the consensus is reached, it is final. Means that it's absolute secure. But if you use classical NC, then there is always a small probability that it can be revoked. Well, but people considering POW like Bitcoin is already safe, so it's don't make too much difference. But in some scenario, like legal sensitive stuffs, or for example, for scenarios in cross-chain or storage, it is a bit inconvenience to use classical NC. So a lot of blockchains now have the finality mechanism. that comes to the secure in our surface is that we also provide a finality mechanism in surface. So in the future, it would be like a block will be confirmed in 4 or 5 blocks time. So within a minute, it will be confirmed. And the confirmation means it is even more secure than the old PoA and than most POW algorithms. And then after like 30 blocks, so 5 minutes, it will be finalized, means it achieved absolute security. Well, to conclude, so PoA 2.0 service, what we try to do is we put the bandwidth usage to the limit. So no, the TPS doesn't matter because it is shown that we really used up all the bandwidth, so it wouldn't, any algorithm wouldn't perform better given the same network condition. Well, and it will have lower latency because of we introduced the committee. And then we also provide finality. And if we compare that to the finality mechanism used in Ethereum 2.0 or Polkadots, we use the really asynchronous BF. We achieve asynchronous BFT, means if a block reach finality, it's absolutely safe. Well, that's all. Thank you for listening.
Okay.
So
it's the Q&A time. I already see 4 questions raised in the by people. So the first question is about people asking why we don't do public KYC for the authority master nodes. I mean, there's thing called privacy, and a lot of the companies and individuals, they don't want to put their information as a public information. So we have to respect that. Also, he's asking, so how can the VChain Foundation make sure that blockchain is decentralized enough? How can we make sure that it is not controlled by one company or 2 companies? I think this question, I think VChain Foundation is supervised by the steering committee, the board of steering committee, and it is a group of 7 people. I'm also sitting on the board. There are 3 people from VChain and 2 executives from DMVGR. We have a lawyer, and we have independent university professor. So I guess this group is diversified and should have enough integrity. So I think I'm quite confident that with the supervision of the current steering committee, we can make sure everything goes well. Also, I just confirmed with our colleagues that it's if only one company can only have one master node, so you can't have multiple master nodes for one company. So also I want to mention that, think about that, holding a master node, holding a authority master node is not like holding, it's not like making a huge amount of money. So what is the incentive for companies to holding a lot of authority master nodes? So I mean, they are running their business on VChain Thor blockchain, so they want to make sure everything goes well, and anything bad happen to the blockchain will be disastrous for their business. So I think this is a unique incentive scheme provided by VChain. So I think that should be my answer to your question. So Wooly asked, will VChain have more than 101 authority master nodes in future? I think in near future, we don't see there's any increase to that. So we have to maintain a certain level of decentralization, but we also need to make sure the network is working fine. The blockchain network is working fine, and we have a sufficient amount of TPS. So another question is, what sort of TPS do you expect to achieve with PoA 2.0? I think Max has already mentioned, it depends on what kind of network you are apply the PoA 2.0. Max, you want to say anything more?
Well, we will test that actually, right? We would test that in the future in the test net to see what would have, but it will, yeah, it's the TPS don't mean too much. Like, uh, I really don't know the exact number, but it will be better than now, and I think it will be better than most, well, I think all public blockchains as decentralized as we are. So, yeah, is the answer. I don't know the exact number.
Yeah. Also, I want to add that is we haven't implemented PoA 2.0, so we don't exactly know what is a TPS is, but theoretically it should perform better than PoA 1.0. So we would expect the theoretical TPS will be better. Okay, so yeah, next question is, can you give an actual project example that uses MTT feature? I think if you check our block, check our browser, if you go to just click one block and check the transactions, you will see a lot of them are MTT. So that means people are using that. So the number of clauses is much higher than the number of transactions. So yeah, everybody's using MTT. So will steering committee regularly decrease the chance? So the next question is, will steering committee will regularly check the chance of authority master to the chance of collusion? So they will check, the question will be, I guess, so asking whether steering committee will check the authority master they're colluding. Will this be up to the companies holding the master nodes? I think one of the advantages of PoA is that the steering committee have the control. So if they found some master node they are doing suspicious or malicious activities, they can respond quickly. They can disable their the power to generate new blocks. They can take them offline. So I think that should be answer your question. What has been the greatest challenge in growing the governance model to be in line with business customer needs? Okay, so I ask this question again. So the biggest challenge is to convince our business partners, say, okay, we have a strong governance. This governance can support the growth of this ecosystem, and they have to believe that this governance, once we put there, once they move their business on this feature, so they can keep running their business as long as they want. So that's the biggest challenges, and I think our PoA, the VChain governance did a quite good job. I think you have seen a lot of the companies already on board, and I think they are convinced with the governance in VChain Thor. So is there any project that benefits from PoA like Walmart or other projects? I think every project benefits from PoA. So the VChain Thor is running based on PoA. So as long as the project is running on VChain Thor, it is benefit from PoA. So do you have any further plan on PoA updates? I think I can give you the current status of the development inside VChain team. So I have already prototyped the PoA 2.0 as I tweeted, I think a couple months ago. Our technical team, our blockchain development team is working very hard to implement PoA 2.0. I think you can check GitHub to see the current progress. Later on, we will apply the new consensus to the testnet first, and we want to make sure everything is safe and most of the bug can be fixed. Then we will decide whether we move PoA 2.0 to the mainnet. I think that is the current status.
Maybe add a few things. It's we are planning to do that in 2 steps, right? So first we will just split that into 2 how to say that, VIP. So first we add the committee-based endorsing mechanism, and then we will add the finality mechanism. So just a little bit more information about our status of PoA upgrade.
Okay, so the next question is how soon can you reapply for authority node? I think, and so how soon? Okay, someone has removed the previous questions. So how soon can you reapply for authority master nodes of your get denied? If you get denied, okay. So that question you can ask our team, our foundation team. I don't have a direct answer to that. You can contact them to email, and they will answer your questions. So is PoA upgrade needed or required, or is it just for long-term purposes? I think so. As more and more business on board on VChain, so I think the upgrade is necessary in my opinion, because we want the PoA to be more secure, to be more stable, to have a higher performance. Also, the new feature would be very nice. For example, the faster transaction confirmation can make business much easier for them to build applications. Also, the block finality is also very important for some applications which requires very high level of security. Block finality can provide the vital needs for them to really build an application. So the next question will be, will the size of the steering committee increase as more companies join the network and the better governance is required? Theoretically, yes. If any of the steering committee member propose that we should increase the size of steering committee, then we can discuss and we can put on a vote. But at the moment, I don't think the size will change. The more company join the network, the better governance is required. I think we already have a pretty good governance structure there. So in my future webinar, I will talk about governance, blockchain governance. I will also talk about our VChain, the governance inside VChain. So I'm confident that current structure of the governance can support the growing business, can support more companies to join our network. So what's your thought on sharding and applying it on VChain blockchain? Would it need to be implemented in future at VChain, or does PoA 2.0 solve a lot of potential bottleneck issues? So you'd like to answer this question, Max?
Yeah, I can answer. I can answer this question because I actually knows I used to write a paper about sharding. Oh yeah, so first of all, I think, well, at this moment, if we use PoA 2.0, yeah, so we could already solve the scalability problem for large margin, so we don't see a emergent need of a bottleneck, so a TPS crisis. But in the future, well, basically sharding and other off-chain approach, known as a scale-out approach, but the problem of that is sharding approach or off-chain approach always sacrifice decentralization or security to achieve a high throughput. So if we really need a really high throughput for some application, we could think about using sharding. But in my opinion, off-chain approach would be a better solution to that cases for that scenario. But if we really need that, because we don't want to sacrifice our security or decentralization in general, so we are not currently considering about directly using sharding technique on PoA 2.0. So that would be my answer.
Yeah, I want to add that, whether or not using particular technologies really depend on the real needs. So at the moment, we don't have the real needs for sharding. And also, you can think about, as Max already mentioned, the sharding, you can think about sharding as like running multiple copies of the same system at the same time in parallel. So it doesn't really make sense now for VChain Thor. So we have a mainnet, and still we don't see there's a major congestion on the network. So we still have the capacity to run more transactions, to get more companies on board. So I don't see in near future we're going to apply sharding on VChain Thor. So I think that's the last question. So surface optimizes.
Oh, yeah.
Go ahead, Max.
No. I'm okay. The surface optimized block validation throughputs are improvement possible for implementation of smart contracts. Are improvements possible for implementation of smart contract on VChain blockchain? Okay. This might not be my. Peter, do you want to answer this question? We have already made several
possible for implementation of smart contract on VChain blockchain. So I think you're talking about smart contract. That's a different level of problem. I think the implementation of smart contracts on VChain Thor can be improved by other ways, but not consensus. I think consensus, the main task is to make the